This chemical weathering reaction turns out to be climate dependent. And it's climate dependent in two interesting ways. First, like any chemical reaction, its kinetics are dependent on temperature. That just means that as the temperature warms up, the reaction happens more quickly. And you can think about this as just if you were to take a rock and react it with acid in the laboratory, its reaction rate would be a strong function of temperature. But another factor also influences its reaction rate, and this is how much water is flushed through the system. You could think about this as if you were reacting in the laboratory a column of ground-up rock with acid. In one situation, imagine if you poured some acid over the rock and let it sit. In the other situation, imagine if you continued to pour fresh acid and it filtered through the rock and you collected the used acid at the bottom, and you continued to pour fresh acid through. Clearly, the one that has flushed acid through it would react much more quickly because it's not ever reaching equilibrium. It's constantly supplying fresh acid to react with the rock. That's basically the same way that the Earth system works as rainwater percolates through the soils and reacts with rocks in the soils. If you have very little rainwater and the water just sits in the soils, it will react with the rock, but will eventually reach equilibrium as you use up some of the acid. On the other hand, if you're constantly flushing water through, carrying the calcium and magnesium away and adding new water and new supply of acid, the reaction rate will go much more quickly. And so there are two ways that climate can affect this reaction rate. One directly through temperature and the other through the amount of water that's flushed through the system. The net result of this is a kind of a thermostat. So think about what would happen if the carbon dioxide in the atmosphere were to start to increase because of volcanic outgassing. If we cranked up the release of carbon dioxide from volcanoes, this wouldn't happen very quickly, but slowly carbon dioxide would start to build up in the atmosphere. If this occurred, the Earth would heat up. And if the Earth heats up, then we would expect to see warmer temperatures in these soils all over the world, and also more intense rainfall. As both of these occurred, the rate of chemical weathering would start to increase. Eventually, the chemical weathering rate would increase enough to balance the higher rate of volcanic outgassing, and you'd be at a new equilibrium, where the inputs of carbon dioxide from volcanoes is once again balanced by the burial of calcium carbonate on the seafloor. Similarly, if the Earth ever got too cold, chemical weathering would slow down, and the volcanic release of CO2 would build carbon dioxide levels back up to a steady state that would sustain liquid water and sustain the weathering rate required to keep the system in balance. So, over long periods of geologic time, this chemical weathering reaction creates a thermostat that regulates the Earth climate. One application of this idea of the chemical weathering thermostat has to do with the faint young sun. Our sun is a main sequence star. What that means is that it actually takes hydrogen and converts it to helium in its core through a nuclear fusion reaction, and that's where it gets the energy that releases all of the radiation that keeps the Earth warm. We know that all main sequence stars over time gradually get brighter as they age, and the reason for this has to do with where the fusion reactions occur inside the star. What happens is that as a main sequence star ages, its core becomes bigger and bigger as hydrogen is converted to helium. And so as you accumulate helium in the core of the star, the fusion reactions move closer and closer to the surface. And as a result, the star gets brighter and brighter. The way that affects the Earth's radiation budget is that we think that 4.5 billion years ago, when the Earth was first formed, the sun was about 30% dimmer than it is today. This is called the faint young sun. The challenge is to understand how was Earth's climate sustained back then. If the sun was 30% dimmer, we would expect the entire Earth to be frozen. And yet we know that it wasn't. As early as 3.5 billion years ago, we have evidence for sediments, we have evidence for liquid water on the surface that would have been impossible if the entire Earth was completely frozen with such a dim sun. The answer probably has to do with the carbon cycle. If we think about the Earth over the last 4.5 billion years, what we can do is plot the solar luminosity relative to modern. We can see that roughly it increases by 30% over that time period. On the other hand, we can also plot the partial pressure of carbon dioxide, and this is on a log scale, and we believe that it decreased over this time period from very high levels back early in Earth history to modern levels around pre-industrial 280 parts per million. This slow decrease over time is probably a direct response to the solar luminosity. The mystery is, why should the Earth's atmosphere know that the sun is getting brighter and react by reducing carbon dioxide? The answer is this silicate weathering reaction, this chemical weathering process. Think back a few billion years in Earth history. As the sun gets brighter, the natural reaction would be for the climate to heat up. But if the climate were to heat up, chemical weathering would increase and carbon dioxide levels would get drawn down. Again, the rate of chemical weathering must always balance the rate release of carbon dioxide from volcanoes, and so a new steady state would be achieved with a lower level of carbon dioxide. So the higher chemical weathering wouldn't persist, it would just increase temporarily until a new steady state was achieved where once again the volcanic outgassing of CO2 was balanced by the chemical weathering, but now at a cooler climate as the solar luminosity increased. So essentially, the carbon dioxide feedback allows the Earth to stabilize the climate as the solar luminosity increases. So rather than the Earth just heating up higher and higher through time, in fact, the carbon dioxide feedback through chemical weathering allows the Earth to maintain a more stable climate even as the sun gets brighter and brighter. One of the most spectacular examples of how the silicate weathering feedback results in a kind of a thermostat that regulates the Earth's climate is something called the Snowball Earth. In the 1960s, a scientist named Mikhail Budiko was developing some of the first generation of early climate models. These were very simple energy balance models that he was using to try to understand how different factors affected Earth's climate. He was actually working for the Soviet military to try to understand what would happen if we had a thermonuclear war and we exploded too many nuclear warheads, resulting in too much dust in the atmosphere and a dramatic cooling of the climate. What he realized was that there was a runaway instability associated with the Earth's albedo. As we've discussed, ice can have a positive feedback on the Earth's climate by reflecting more sunlight back to space. Think of it this way. If you have a small polar ice sheet at high latitudes, it locally makes the Earth a little bit colder by reflecting more sunlight. This is one of the factors that amplifies the Milankovitch cycles and leads to the Pleistocene ice ages. But think about what would happen if the ice sheets started to grow even more. As the ice sheets move from the pole down towards the mid-latitudes, their impact on the Earth's overall albedo becomes much greater. First, because there's more area as you move away from the pole, and second, because the incidence of sunlight is much greater. The mid-latitudes get a lot more direct sunlight than the poles. So as the ice moves from the pole towards the mid-latitudes, its effect gets greater and greater, and it cools the climate more and more. What Budiko realized in the 60s was that if the ice ever extended down to something like 30 degrees north and south, you would have a runaway situation where the impact on the climate would be so great, you'd be reflecting so much light back to space that the temperatures would plummet and the ice would quickly extend all the way to the equator. This is a state we call the Snowball Earth. Now, Mikhail Budiko thought that this would never occur, that the Snowball Earth was an impossibility because what he realized was it was so stable. The temperature would be something like minus 50 degrees Celsius, and it would just sit there forever. It was so stable that nothing could ever melt the ice. And because we are currently not in such a situation, Budiko reasoned that this would never have happened throughout Earth history. It turns out that Budiko was wrong because he didn't understand the carbon cycle. From what we already learned about the carbon cycle, we know that the climate is stabilized by greenhouse gases, carbon dioxide coming out of volcanoes, balanced by carbon dioxide buried in sediments, both as organic carbon and as calcium carbonate through the silicate weathering feedback that also releases nutrients for making organic carbon. Now, this is what Mikhail Budyko didn't really understand. If you ever had a snowball Earth, think about what would happen to silicate weathering. If the Earth was almost completely frozen, even if there were a few holes in places where there were volcanic activity, you would still have carbon dioxide coming out of volcanoes. First of all, a lot of the volcanoes are actually under the ocean and they would continue. But in addition, the volcanoes don't really care about the temperature on the Earth's surface. If you plunged the Earth into a snowball state that persisted for millions of years and you just waited long enough, eventually the volcanoes would put enough carbon dioxide in the atmosphere to melt back the ice and restore the Earth's climate balance. Climate modelers have calculated that it might take 100,000, maybe even 200,000 parts per million of carbon dioxide to actually melt back a completely frozen planet. It depends a little bit on exactly how white the snow was, how dirty it was with dust. But it seems like in a few million years, possibly as long as 10 or 20 million years, there would be enough carbon dioxide in the atmosphere to melt the ice sheets. Now imagine what happens when the ice starts to melt. In the beginning, the ice would first melt at the equator where the Earth is warmest. And by melting a little bit of ice at the equator, you'd begin to see dark seawater instead of white ice. And the effect on the Earth's climate would be dramatic because, of course, the equator absorbs a lot of heat. That would drive more melting of ice. What you can see is that this runaway albedo feedback would actually start to work in reverse. That very quickly you would go from a completely frozen planet to a completely ice-free planet, but now with 100 or 200,000 parts per million of CO2. This is what we call the freeze-fry cycle, a very cold climate rapidly converted to a very warm climate. And it's exactly what's predicted from the theory of silicate weathering that we've discussed. You can put all of this together in this simple figure that describes the freeze-fry cycle in a very simple way. This is a graph showing the latitude of ice on the y-axis. It assumes a symmetric ice sheet in the northern and southern hemispheres. And on the x-axis, it shows the radiative forcing. You could think of this as a change in the solar flux or as the concentration of CO2, in this case, the log of the concentration of carbon dioxide. The world today sits in a state where there are some polar ice sheets on Greenland, in Antarctica, and of course, the Arctic used to be mostly covered with ice. It still is in the wintertime. From its current state, the ice sheets can melt and retreat a little bit poleward or a little bit equatorward, but still be stable. That is, they won't be in a runaway situation. But if you were to ever extend the ice sheets to about 30 degrees, what you'd see is that suddenly you enter an unstable region where the radiative effect from the albedo on the Earth's climate is so great that it would plunge the Earth into a completely frozen state. And that's also very stable. That's shown here in this lower line, where the Earth is completely stable, completely ice-covered. And it would require a very large amount of radiative forcing, either a much brighter sun or much higher greenhouse gas concentrations to actually begin to melt it back. But if it ever were to happen, what would happen very quickly is that you'd switch from one stable state of completely ice-covered to the third stable state, which is completely ice-free planet, where all of the ice would disappear very, very quickly, and you would now be completely ice-free, but with very, very high carbon dioxide concentration. In that very warm climate, it's the silicate weathering feedback that would actually restore the balance. Think about what happens in the aftermath of a snowball Earth. The glaciers have been grinding up the rocks for millions of years, but it's been so cold that there's been essentially no running water and very little silicate weathering happening. And so all of this ground up rock with intense heat and lots of rain that's very acidic because of the very high concentrations of CO2 would react very quickly. And in probably just a relatively short time of tens of thousands of years, you would draw the carbon dioxide back out of the atmosphere and turn it into calcium carbonate sediment on the seafloor. So it's the silicate weathering feedback that ultimately saves us from the snowball Earth state. Now, the most interesting part of this story is that we actually think this occurred in Earth history, not just once, but possibly twice towards the end of what's called the Neoproterozoic period, between about 750 and about 600 million years ago, and possibly twice as well, much earlier in Earth history, around 2.5 billion years ago. The more recent time period, the Neoproterozoic, there's a number of fascinating geologic observations that suggest that the snowball Earth occurred. First of all, we see evidence for glacial rocks, what are called glacial tillites, rocks that could only be formed by moving glaciers on land. And they occur on every continent today, and many of them can be shown to have occurred near the equator. At least at that time they were near the equator. This is from the magnetic signature of rocks. We can reconstruct where those rocks were relative to the magnetic field of the Earth at that time. There are many other strange geologic observations that can be best explained by the snowball Earth hypothesis. For example, we see the reoccurrence of banded iron formations, deposits that we think form from dissolving iron in seawater. Since about 2 billion years, those iron formations are very unusual because the atmosphere was oxygenated, and yet they reoccur during these glacial deposits. We think this was because the ocean was covered with ice and they couldn't absorb the oxygen as efficiently as they do without all the ice cover. And one of the most spectacular observations associated with these Neoproterozoic glacial deposits is that they have what are called cap carbonates. These are thick layers of calcium carbonate that occur directly on top of the glacial tillites. This is very unusual because at this time, carbonate rocks generally are associated with warm climates, and you see this very funny juxtaposition of rocks associated with glacial conditions immediately overlain by thick carbonate rocks. This is consistent with the sort of freeze-fry conditions that we've discussed. The very cold snowball with an ice-covered Earth, followed by a very abrupt transition to a very warm climate that persisted for quite a long time.